there's a very clear features to label mapping relationship from the previous fish classification task. So in the training data, we use feature or feature vectors to represent the data points. And we have a label. It could be a binary label. It could also be a continuous label or even multinomial labels to describe the task. So given any new task example or task data points, as long as we can compute the feature vector, then we can use the feature vector to predict the label, given the data we already trained. So the example or this paradigm extends to a lot of other examples. So let's go through a few examples here. For example, here, the flower classification task. It's a very famous data science data sets in UCI. And the task is to provide a type of a flower, which has 3 categories. And the features used are 4 real number features: the sepal length, width, petal length, petal width. So the feature vector has 4 elements, and the length of the feature vector is 4. The second example here, to predict the autistic spectrum disorder, then the feature vector is much longer. It has 21 features, and the task is also a binary classification to diagnose whether a person has positive with ASD or negative. Okay, so feature vector is 21. So including gender, ethnicity, age. So the feature is a very diversity in types. So it has binary features, also string features, also real number features, integer numbers. So another very famous example of recognizing the handwritten digits numbers, the task becomes more difficult because we want to recognize from 10 categories, from digit 0 to digit 9. And the feature is also much larger, in a larger space, because we represent the image with pixel values. So depending on the size of the picture, and if we convert the a 2D image in a matrix of pixel numbers, then we can flatten that image into a very long vectors. So in this case, the vector could be very long. The last example, insurance company, it also uses a lot of features to predict the age of individuals. And the example here is a very typical regression question, because the target variable to be predicted is a real number, continuous number. And also it can, the insurance companies also wants to predict, depending on what the business is, it can predict the ripeness of fruits and so on. Okay, so much examples we have introduced about the supervised learning. And one characteristic of supervised learning is that we map the feature to a clearly defined label. Okay, so we have the training data are feature label pairs. Okay, and the task examples has only features. The task is to predict the label from these features alone. Okay, and on the contrary, in unsupervised learning case, the training data does not include labels. It only includes features, or we say it is unlabeled. And the task is not to find the mapping relationship between the feature and the label, but to discover the hidden patterns in data, like whether the data can be grouped into clusters, or whether the data can be better explained if we reduce the dimensionality. Okay. So in the chart here, I think it explains the difference between supervised versus unsupervised learning in a very visualized way. So on the leftmost charts, we represent data with basically each data point or each instance is a row vector. Okay, so this is a row vector. We call it a one data points. And the first couple of columns, they are the features. Okay, and the last column here, the last column is the label. Okay, so that's usually how we can place or how we can organize data, organize training data in a supervised learning task. But for unsupervised learning, in the middle, the data point, the data instance is just one row. And there's no column label here. All columns are features. And here we introduce an interesting case somewhere in between, which we call semi-supervised learning. Okay, so the training data is a mixture of heterogeneous. It's a mixture of labeled instances with unlabeled instances. So the labeled instances is pretty much like the part here. And the second part is pretty much like the unsupervised learning data set here. So here we got labels. The upper half we have got labels, but the second half we didn't have any labels. Okay, so that's pretty visualized way, a pretty nice visualized way that you can use to memorize the differences between supervised versus unsupervised learning. So more examples like this. So I will use this example as a comparison or the contrast between supervised versus unsupervised. We mentioned that iris flower data sets. So if the data, if we keep the flower category column in this case, then if we visualize the plots here, each group has its own labels, right? You can tell from the colors. What if we remove the labeled columns? Then the data, if we plot them in the 2D space, it looks like this, right? It's hard to tell apart those that are grouped together, right? We only see that these parts versus these parts, right? So this is a demonstration for when unsupervised learning looks like if we don't have labeled information. All right, so a simple recap. We've spent some time talk about the data representation steps that are necessary to conduct machine learning tasks, and also we use examples to tell how the supervised learning task is different from the unsupervised learning task. But one thing in common is that they all need to, no matter whether supervised or unsupervised, they all need to represent the data in a reasonable way. By that I mean we need to select our features carefully. Okay, and in some other types of machine learning tasks, like the reinforcement learning or semi-supervised learning, I think as long as there's learning going on, the data representation is always an issue or always a topic that is worth discussing.